Hi everyone, welcome to our presentation for the project of this deterministic models in operation research course. As you can see from the slide, our group have five members: Phương Hoàng, Ngọc Linh, Tú Quyên, Tố Nhi, and me, Tuyết Ngân. And our presentation will give you a clear view of the problem we dealt with. So without any further ado, let's begin. Our presentation will be divided into 7 parts: introduction, methodology, problem statement, problem solving. The next one is sensitivity analysis, practical application, and the last one is conclusion. Now let's start with the introduction. Alongside the recent rapid development of advanced technology, we have all witnessed worldwide integration, which would bring about chances for countries to learn from each other as well as to improve their own living standards, especially the developing ones. And in order to do that, many things are in need of improving. For instance, business development and production process. These two actually account for a huge proportion of a nation's economy. Therefore, optimization is required to be applied as much as possible since it has been the key factor in advancing one's way of operating business and production. And at this point, when it comes to optimization, the knowledge from the OR course would be fully applied. In terms of optimization for the future purposes, countries are urged to solve the problem of task allocation for production process, one of the most common yet complicated issues. On a large scale, this mentioned issue may be quite enormous to be dealt with by some simple algorithms. Our problem would be narrowed down to allocation of specific targeted buyers to each single suppliers. Solving this issue may give us a broad base on how things will work on a larger scale where the data can go up to million units. And in order to cope with task allocation, several methods are available to use. However, as the purpose of this model directly relates to the logistics and supply chain management, where optimization is a priority, linear programming and integral programming are highly recommended. Not only these two are straightforward, but they will also provide desired results with high accuracy. Moreover, so as to apply these methods at the finest, support of Cplex, a modeling software, would also be utilized. It provides appropriate outcome and has a simple interface. And for further description of the model, let's move on to the next one, problem statement. Optimizing cost of production plants with a plan to scale back to 500,000 units and saved 40% of the fixed cost to fully serve the demand of four markets in Blossom. And the problem here, we have a table showing the markets of the proper Blossom company. We have four markets: South Asia, China, Japan, and Korea, with the annual demand of 200,000 units, 400,000, 250,000, and 500,000 units respectively. And as for the plans, we have a total of three plans: China, Vietnam, and Malaysia. Their fixed costs are $1 million, 3 million, and 250,000 million dollars, and $2 million for Malaysia. The variable costs are $8 per unit for China, $12 per unit for Vietnam, and $10 per unit for Malaysia. And their capacity are also different. That is 700,000 units for China, 800,000 for Vietnam, and the last one is 600,000 for Malaysia. And as for the limitation of this project, the problem is narrowed down already, and in reality, it may be influenced by many other factors. For example, tariffs, additional fees, production rate, or even political issues. All of those factors can directly affect the way we build the function as well as variables. And for the objectives, as this problem includes different types of cost, the main purpose in building the models is to minimize total cost incurred and to optimize the allocation for plants and markets. Next up will be the mathematical model. Next up, Bao Huang.
First of all, we define a mathematical problem with decision variable and objective function. In decision variables, with I is plain and j is market, and Sij is quantities planes I supply in for market j, and two binary variables are Yij equals to 1 if I serves market j and equals to 0 in the other ways. And yet I equals to 1 if plane I scaling back and yet equals to 0 in otherwise. We also define other components for integer. N is the number of planes, M is the number of markets, and with equivalent range is 3 and 4 we point out. Ki is capacity of planes I, Bi is variable cost of planes I, and Dj is demand of market J. Fi is fixed cost of plane I. So in objective function, we try to define the minimized cost to figure out which plane serve which market. Let's say plane I serve market J with two cases. If plane I scaling back to 500,000, then its fixed cost reduced by 40%, and total fixed cost of three planes is calculated, plus X amount of product that plane I will supply for J, multiplied with variable cost of plane I. If plane I doesn't scale back, then our fixed cost stay the same plus with X amount of product that plane I will supply for J, multiply with the variable cost of plane I. And in the first constraint, if capacity of plane I is scaling back, yes equal to 1 and Ki equal to Ki minus 500,000. If not, yet equal to 0 and capacity of the plane I remain the same. In the second and final constraint, the total products that plane I supply have to be larger or equal to the demand of market J and smaller or equal to the capacity of plane I. Therefore, we write down the simplex code like this and represent it by doing.
For this problem, we use Simplex Optimizer, which provides for high-performance mathematical programming solvers to find the best solution for our project. As you can see on the screen, after applying in the components, decision variables, objective function, and constraints as in mathematical model, we run Simplex Optimizer and gain the solution. Next slide. Plan 2 will be scaled back to 500,000 units to save 40% in fixed cost. Plan 1 serve market 1, 2, and 4. Plan 2 serve market 3. Plan 3 serve 3 and 4. The mean total cost is $17,150,000. Then we apply sensitivity to investigate the effect of parameters on the optimal solution in the linear programming problems. Since we already know which plan I serve which market J in Xij from the solution below, we enter x11, x12, x14, x23, x33, and x34 respectively as x, y, z, t, rv into Lingo. Then we found out the allowable range of the coefficients in the objective functions is for x11, it comes from -2 to infinity, x12 from 2 to infinity, x14 from negative infinity to 10, x23 from 10 to infinity, x33 is from 0 to a, x34 is from 8 to infinity. Also, we gain allowable range for the right-hand side in the functional constraints. In constraint 1, it comes from 600,000 to 1,100,000. In constraint 2, it comes from 0 to infinity. In constraint 3, it comes from 650,000 to infinity. Comes from 0 to 300,000. Constraint 5 is from 0 to 500,000. Constraint 6 is from 0 to 400,000. And last one, constraint 7 is from 100,000 to 350,000. So to continue, let's go through some practical application represented by Lin.
Good morning, Ms. G. I'm Lin, and I will present the practical application of our project. The formula that we have built could be applied to solve plans with many decision variables, especially in planning the supply chain of factories or markets, which is required to be optimal with the lowest cost and time. Considering the application of the problem and model in real life, we will take the Vietnam Dairy Product Joint Stock Company, which is normally known as Vinamilk, as an example. The main product of the company are fast-moving consumer goods, which are supposed to be sensitive in the consumption market. As a result, the issue of how to transfer that product fast and correctly in position becomes significant. In reality, there are 3 factories with warehouses of Vinamilk Company in Ho Chi Minh City, and their daily activity is keeping the supply chain of product running smoothly and maintaining the balance between stock and order for the 3 warehouses. We can simplify this case related to the project that the 3 factory and warehouse of the company are brands and retailers that purchase products from Vinamilk or markets. Team applying the model in this case could have the company find the optimal solution at which warehouse will fit to transfer the goods to which retailers. However, in this case, the market could be up to 1,000 points and constantly change every day. Consequently, it has set a huge difficulty in collecting information for building mathematical planning. Besides that, C software could take a lot of time to show thousands of variables at the same time. In the following part, we will present the conclusion of the report.
Finally, I will wrap up our presentation. This project in general has offered a good demonstration of how deterministic models in operation research course can be applied into reality. Not only can small problems be applied, but large-scale issues of companies and corporations, in which data can reach thousands of units, can also be converted into specific mathematical models through decision variables and constraints. In particular, analysis of management and process performance in factories would be well handled thanks to the application of this course. Moreover, optimization in finding the result would also be reached more easily with high accuracy by the help of some modeling softwares such as Cplex or Lingo. This is the end of our presentation. Thank you for your listening.